You've already mastered most of the charts and tables in the performance section of your Skyhawk's POH or PIM. So now let's whip through the remaining 3 charts so you'll be able to find out almost anything you need to know, except perhaps the location of a good restaurant at your destination. First, you'll look at takeoff performance. Notice that this chart is entitled Short Field Takeoff Distance. To get the performance shown, you must employ the short field technique that you'll study in your next flight lesson. Let's apply the same conditions you used in a previous lesson and run through an example. We'll use a pressure altitude of 2,500 feet and a temperature of 25 degrees Celsius. Add to that a headwind component of 18 knots that you worked out from the wind components chart, figure 5-4. Now, as you look at the takeoff chart, you'll see pressure altitude here, and across the top, temperature. That's right, it's another density or performance altitude chart in disguise. Once again, instead of printing the value of the density altitude, the engineers plugged in the performance you can expect at that density altitude. Remember to keep your results conservative by applying the next higher temperature and altitude values, rather than interpolating. It also keeps the arithmetic simple, and if we pilots need anything, it's simple arithmetic. So, at 3,000 feet pressure altitude and at 30 degrees Celsius, the next higher values above our examples of 25 degrees Celsius and 2,500 feet, you read a ground roll of 1,400 feet and a distance to clear a 50-foot obstacle of 2,540 feet. We're going to read the footnote because you want to decrease distances 10% for each 9 knots of headwind. That's a performance benefit of 10%. And with 18 knots of headwind, it means that you're entitled to 2 of those 10% performance increment bennies, or a total of 20%. Okay, let's do some math. To get the ground roll, you're going to take 20% of 1,400 feet, which is 280. Subtract that 280 from the 1,400 feet, and you end up with a distance of 1,120 feet for the ground roll. Now, to find out the distance that you need to clear a 50-foot obstacle, you take 20% of the 2,540 on the chart, which is 508, subtract 508 from the 2,540, and you end up with 2,032 feet, the distance to clear a 50-foot obstacle. And that's all there is to it. A short field takeoff is a whole lot of fun and safe to practice from the runway you're used to. You can pretend that the end of the runway is the 6th runway light from your starting point, and the 50-foot obstacle is an imaginary line extending from the hangar roof. But you should have a very good reason before putting yourself in the position where you must get the charted performance and not the tiniest bit less. Just for the heck of it ain't good enough. Imminent nuclear attack might be a more reasonable motivator. So does this mean you shouldn't use this chart? Well, goodness no, it can be an excellent confidence builder and even a decision helper. For instance, you might find yourself at an unfamiliar airport and you're not sure how well you or your Skyhawk will fare. Just perform the short field calculations, and if the available distances are about 50% greater than what you calculated, you can depart and not give it another thought. If, on the other hand, the available distances are only 25% or so better than your calculations, you should probably do something to stack the deck in your favor. Wait till it's cooler, take on less fuel, things like that. Mastering short field landings is another tool for your bag of tricks, and the good news is that figuring the distance is handled exactly the way as with takeoff. If you can do takeoff, you can do landing. However, in your euphoria, don't overlook the whopping performance penalties in notes 3 and 4, especially the one that reads, for operation on dry grass runway, increase distances by 45%. Before using the landing chart, first check the takeoff chart. Comparisons will show you why. Your Skyhawk needs a lot less distance to land than to take off. If you don't give some thought to takeoff prior to landing, it's possible that the only way your Cessna will get airborne again is dangling from a cable beneath a medium-lift helicopter. Now here's a chart you'll employ when you start flying cross-country. It's called the Cruise Performance Chart, and it's a snap to use, and it doesn't require the computation of either performance benefits or penalties. And while it still has pressure, altitudes, and temperatures, which scream density altitude at you, it has a different wrinkle that should be immediately obvious. It's the form of the temperature entry. You're given a choice of 20 degrees Celsius below standard temperature, and 20 degrees Celsius above standard temperature. Obviously, you'll need to know what standard is. That's where the standard temperature column in figure 5-7 comes into play, just like we promised you. Let's use the same 7,500-foot cruise altitude that we've used before, and this time a temperature of 12 degrees Celsius. How do you know what the temperature is at 7,500 feet before you get there? Well, winds and temperatures aloft forecasts are available, and when you study weather, you'll learn how to get them. For now, just assume that you got the info and it turned out to be 12 degrees Celsius. In figure 5-7, there's no listing for 7,500 feet, but by comparing the temperatures at 7,000 and 8,000 feet, you can determine that the standard temperature there is 0 degrees Celsius. So your temperature must be 12 degrees hotter than standard. Since 8,000 feet is closest to 7,500 feet, and 20 degrees above standard is closest to 12 degrees, we'll use this area of the chart. Now, the next step is completely up to you. Can you imagine? You actually get to make your very own decisions. Choose one of the variables along a horizontal line, like 2,200 RPM, and accept the values of the other three. There are reasons why you might select any one of the four variables. Some examples might make that clearer. Suppose you'd like to keep the cabin noise to a minimum for your passengers' comfort, but you'd also like a reasonable speed too. In this case, you could compromise on 2,200 RPM. As you can see, this yields 61% power, 107 knots, while burning 7 gallons of fuel per hour. Or you may have noticed that the range and endurance profiles, figures 5-9 and 5-10, suggest that 70% power offers a good balance between range and the time you need to get there. So, if you choose 71% power here, you'd need 2,350 RPM to get 118 knots with a fuel burn of 8.2 gallons per hour. You could choose any specific airspeed or fuel consumption rate for similar reasons. That's up to you. Just pick your variable and read the other three. And speaking of picking, you now know how to pick your choice of the performance numbers the factory has given you, which means all that remains is picking a good restaurant, a far more difficult task. Bon appetit!